Welcome everyone, this is Mr. Hyatt, and today I'm discussing isotopes and atomic mass. So here on the screen you see three versions of hydrogen. There are three isotopes of hydrogen. Remember, an isotope is an atom that has an abnormal number of neutrons. So you see that these three each have one proton, so that defines them as hydrogen. They each have one electron as well, so we know that these are not hydrogen ions, these are hydrogen atoms. The difference between the three is the number of neutrons in the nucleus. Let me switch over to P table, and I want to point out that each of these element cards has a number below the elemental symbol that is our atomic mass. So if you notice, those are decimals. Maybe it's 0.008, but they're all decimals. Once upon a time, maybe this year, maybe in middle school, maybe in elementary school, you learned that the number of protons defines the atom, tells you what the element is, and also tells us how many protons and how many electrons in a neutral atom. But then we can also determine the number of neutrons in the atom by taking the atomic mass and subtracting the atomic number. So here we'd take 45 minus 21, so that'd be 24. So there must be 24 neutrons in the nucleus of this scandium, because we know all of the mass of an atom is the protons and the neutrons. The electrons are so small and insignificant that they don't contribute to the atomic mass. Well, that sounds great, and it's usable. We can do some basic subtraction with whole numbers, but we don't have whole numbers. We have decimals. So the purpose of this video is to talk about where those numbers come from. How do we know the atomic mass? How do we know the molar mass? Well, we do averages, essentially. Okay, so again, I just want to show you that picture of the three isotopes. I've got an example I'm going to show you here in just a minute using some fictional isotopes. But again, essentially what we're going to do is we're going to take the mass of this thing right here, and we're going to multiply it by the amount of these isotopes. That's this one, if that makes sense. It's a lot like when you calculate your final grade. Let me show you how that works. I'll zoom a little bit so we can see a little bit more clearly. But if the way that we do grades here at our school, we have 2/5, 2/5, 1/5. So 2/5 of your semester grade is your first 9 weeks. 2/5 is your second 9 weeks. 1/5 is your final exam score. So if I do what's called a weighted average, you can see the equation that I have in my cell or in my formula bar right here. I can figure out what my final grade is going to be. So I take each of those times their weight, which is 2/5, and then I add them up. And that gives me my overall weighted average, which is 70.2. Do you have any classes where they use category weights? Some of my classes use category weights, calculated the same way. 20% of your grade is homework, 20% of your grade is this, 30% is that. Well, you take your score on your homework, you multiply it by 20%, and that gives you your abundance of that grade. If I switch gears and I look at, again, this is a fictional set of isotopes, three different versions of the same atom. So all three of these would have the same number of protons, and if not an ion, they would have the same number of electrons. Only thing that's different between these three is the number of neutrons. So if we look at the atomic mass, if we were, the challenge with this data set is to take this sample that I provide and to determine its atomic mass. What's that number that would go on the periodic table? So what we've got, this is the mass of the total amount of each isotope. This is how many of each isotope were present in the sample. The next row down, row 5 there, average mass of each, I just took the number, I took the mass and divided by the number of each isotope. That percent of each would be similar to your category weight in your weighted grades average or your class average that I mentioned with category weights. So as I move down here, I'm just essentially doing math. I'm multiplying the average mass by the abundance. So how much space does it take up? What's its mass? How much stuff does it have? And how much of that thing is there? That's essentially what I'm doing a bad job of explaining. So for each of the three samples, I'm going to take their average mass and I'm going to multiply them by their abundance, or how much of them there are. That's what this relative weight is down here in row 8. So if you compare rows 5 and 8, row 5 is just the average mass of each of these isotopes. Row 8 is an adjusted average. It's a weighted average. When we sum those together, we get 0.404 grams would be our molar mass. So again, my atomic mass, molar mass, my atomic mass in this case. So I've got 3 different versions of the same atom, the same element. They've got different numbers of neutrons. I average their masses and I add them together. That's how I determine total atomic mass. That's how those numbers on the periodic table are determined. That's why they're all decimals and they're not nice, even, round numbers. You're going to look at this in a couple of different ways over the next week or so. Please let me know if any of this doesn't make sense. You're going to get some practice with it, some practice calculating and things like that. So please reach out if you have any problems whatsoever.